Welcome to Study Loop.
Hey there, this is Josh. Today we are looking at this problem 4410. The first part of this problem says, I want to know what this frequency is, which happens to be twice the normal frequency associated with this type of accelerator. Okay, so applying equation 44.7, we see that for this system, omega equals QB over M. Omega is equal to 2 pi f naught, we'll call, because this is what we're looking for is 2 times this quantity. Okay, let's solve this for f naught. All right, f naught is equal to qb over 2 pi m. And let's call f equal to 2f naught, meaning f is equal to qb over pi m. Now, we can just plug in our parameters here. We know that Q is fundamental charge, 1.6 times 10 to the minus 19 coulombs, times B is 1.7 Tesla, divided by pi, which we can approximate as 3.14. You can plug it into your calculator and give a much more accurate result, times the mass, which is the mass of a proton, 1.67 times 10 to the minus 27 kilograms. And we get a value of 5.18 times 10 to the 7th hertz. Okay, so that's the first part. The second part wants us to find what the velocity of the particle is. Now, applying equation 44.6, we have this relationship. R is equal to mass times velocity divided by Q, we'll use a magnitude here, divided by the magnetic field. Okay, so we have mass from here. This is mass. All right. Velocity is what we're solving for. Charge is here. And then the magnetic field, of course, is here. We already have it solved. Okay, so let's rearrange this to solve for V. All right. Oops. Okay. V is equal to R Q B over M. Simple algebraic manipulation. And we plug in our parameters, I get that V is equal to 4.07 times 10 to the 7th meters per second. Now, if we look at V over C, we get that V over C is equal to this quantity divided by the speed of light, which is essentially 3 times 10 to the 8th meters per second. And that gives us 13% the speed of light, 0.13 c, so it is certainly relativistic. The next part of the problem, we actually have to utilize the fact that this is a relativistic beam, and it is asking what accelerating potential this has to go through to get this energy. Now, when we're dealing with this, the overall energy of a particle is the factor gamma times its rest mass. Okay. And what we're going to deal with here is this gamma mc squared is equal to the kinetic energy, which is the charge of the particle, times the accelerating potential. It's how much energy it gains from the potential, plus the rest mass. All right, now I'm going to solve this for EV on the left. EV is equal to gamma minus 1 times rest mass. Okay. And I get that the accelerating potential is equal to gamma minus 1 times mc squared divided by E. All right. Now, what's going to happen here is we'll see that a lot of things are going to cancel out. First off, this term gamma. Let's go ahead and look at that. We'll do that up here. Make a little cloud for it, a gamma cloud. A gamma cloud would not be something you'd want to go inside, but for this exercise, let's go inside. Okay, so gamma is equal to 1 divided by the square root of 1 minus v squared over c squared. Okay, and for our particular problem, that is equal to 1.009. Okay, now that we have a factor for gamma, we need to figure out what the rest mass of a proton is. So let's do that up here. That's okay, we can really just do it down here. Rest mass for a proton is equal to 938 MeV per c squared. All right, let's go ahead and plug all these things in. I'm going to get that we'll leave this all in terms of variables, 1.009 minus 1.009 times 938 MeV per c squared times c squared, so that's just MeV, divided by E. So the E on the bottom and top cancels. We are left with a potential of 8.4 megavolts. Okay. Okay. Thank you very much.